So we want to talk about molecular geometry, which means the shape of the molecule, hybridization, what orbitals it's going to use, and polarity. Let's start with NH3, which is ammonia. We know from doing dot structures that it should have 8 valence electrons total, 5 from the nitrogen, 3 from each, 1 each from the hydrogen, and we're going to have this Lewis structure. So that's pretty simple. Then we look at the central atom, which is nitrogen, and we say around the nitrogen. What is around the nitrogen? So around the nitrogen we have 3 atoms and 1 lone pair. What we're looking for is how many directions there are electrons going out from the central atom. And it turns out that if we add 3 and 1, we have 4 electron groups going out from the central atom. Oh, well, that's pretty nice. We can look at that. Electron groups can be can be single bonds, double bonds, triple bonds, or lone pairs. So it doesn't matter whether it's single, double, or triple bonds, because those bonds are still just going in one direction. If you have a double bond, it's going towards the other. It's stretching between the central atom and the atom on the outside. So we have, in this case, we have 3 single bonds and a lone pair. Like I said, it doesn't matter what kind of bond you have. But we have electrons going in 4 directions, which means we look on that molecular geometry handout that I posted for you, and you say, oh, 4 electron groups? That must be a tetrahedral shape. Okay, so 4 electron groups, that means tetrahedral. And tetrahedral now is for the electron groups, right? So we're going to say this is going to be the geometry. The way we kind of sketch this is to do like so, where the straight lines are in the plane of the paper. The wedge is coming out at us. So imagine the skinny end of the wedge being in the plane of the paper. But as it's coming at you, if it's coming out the paper at you, it's getting fatter and fatter as it comes closer, kind of a perspective drawing on a small scale. And then we have dashes that mean that thing is really behind the paper. We really, if we're thinking about the paper being here, we really can't quite see that thing behind. So this is the tetrahedral electron arrangement. But our situation is a little different than a tetrahedral molecule, because one of those 4 directions is not an atom. It's a lone pair. So what we have to do with that is, when we arrange these atoms now in that shape, we're going to get something like this, where the 3 hydrogens are in the we're going to make them all the downward pointing atoms. They don't point downward very much, but they do a little bit, and that's enough. So we have a lone pair sticking up above. When we name the shape of the molecule, we don't look at the electron groups anymore. We use the electron groups to decide on the shape, but then when we name the shape, we only use the atoms. And so we look at the atoms and say there's 3 of them. There's 1 going down like this, 1 going down like that, 1 going down like that. And so it looks like a little tripod, a short little tripod. I should have drawn it a little bit more vertical. So the three bonds are going slightly downwards, and so we will call that a very good picture. We will call that a trigonal, because it goes in 3 directions, but it's like a little short squat pyramid. So it's pyramidal. The bond angles in here, if it were strictly tetrahedral, would be 109.5. It turns out that ammonia's bond angles would be 107 degrees. This is 107 degrees. This is 107 degrees. If we could measure the lone pair, it would be more. It would actually be greater than 109.5, and between the hydrogens is 107 degrees. The reason for that is that the lone pair is not stretched between 2 atoms. That lone pair is just only held in, snugged up to the nitrogen nucleus, and therefore it takes up a little more space than the bonding electrons do. If you had that nitrogen in the middle, you would have kind of a bond like this going to each of the hydrogens. It's kind of fat. So we have a hydrogen, hydrogen, hydrogen. So those are kind of the shapes of the orbitals that the electrons would be in. But then this one is kind of short and fat, and he's repelling these bonding electrons. They're pushing away from each other. And so these guys, the bonds are bent down a little more than they would be if that were 4 bonds. Okay, back to our shape. Trigonopyramidal is our shape. We're good for that. Now what we need to do is decide what the hybridization is. A hybridization looks hard, but it's really actually very easy. What we want to do is say orbitals that are possible to bond with would be the s, p, and d orbitals. Well, in nitrogen's case, there aren't any d's because nitrogen's in period 2 and there aren't any period 2 d's. So the only thing we have possible for him is an s, a p, and a p. Okay, we're obviously not using the s, the p, and the p of the atomic orbitals to make a tetrahedral shape of our electron groups because p orbitals are 90 degrees to each other. And this came out 109.5, or in ammonia's case 107. So what I'm going to do now is say I'm going to take all of these guys, I'm going to put them in a bag. Okay, here's my little bag. I'm going to pop them into there, and I'm going to just close up the top and just shake them and shake them, shake them until they come out even with each other. In other words, some of the S mixes with the P, and the P's mix with the S, and so what we're going to get out of there when we take them back out is still four orbitals, but each orbital is going to be 1/4 S and 3/4 P. So we're going to have 4 orbitals, but now they're all the same as each other. They each have some S character. In other words, an S is a fat round circle, and here's my different P's that I'm putting in here. This one's at an angle. It's kind of coming out of the paper. That's hard to show. But what this is going to look like is I'm going to have a fat thing like the S, but 2 lobes like the P. And so look at that. We have a tiny little second lobe on it that usually we don't show when we are doing the geometry. And then we've got another one that comes out like that, and another one that comes out like this, and another one that is coming at another angle yet. So I don't know. I'll put it like that maybe. But their geometry is pointing in the 4 tetrahedral directions. In our case, we have 3 bonds in 3 of the sp3 orbitals, bonds, and 1 is in lone pair, but the lone pair is still in an sp3 orbital. So what you have to do when you decide on the hybridization is simply to count how many directions you have electron groups. We're going back way up to the top here where it said 4 electron groups. If we have 4 electron groups, that means sp3, period, because I have S and 3 P's, 1, 2, 3, 4, that go together to make my sp3 orbitals. So that's pretty simple. If you have 2, if you had only 2 electron groups, you would count just the S and the first P, and that would be it. So it would be sp, because 2 is S plus P is 2. If you had 3 electron groups, you would take the S and 2 of the P's, so you would have S plus P plus P. So it's pretty simple. As soon as you decide that you have a tetrahedral electron arrangement, you know immediately that you are sp3 hybridized. Last thing, polarity. We look at our nitrogen molecule, and I'm going to draw them a little bigger here, and dash, 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 dash going down there. You see, it's like a little tripod, and the nitrogen is at the junction of the tripod, and the lone pair is sticking up, but he's invisible. And what we want to do is say is look at the electronegativity. Nitrogen is more electronegative than hydrogen. So we can show this 2 ways. We can use vectors, which means it's like an arrow with a little cross on the bottom end, and we're pointing from the positive end, so that makes it easy because it looks like the positive, like a plus sign down here, towards the negative end, and towards the electronegative end. And we're going to do the same thing with this bond, and the same thing with this bond. Then when we add up all these vectors, anything in the x direction is canceled out because all three of these are equally spaced around the nitrogen. But in the up and down direction, they don't cancel out. So there's a short, fat little vector sticking up, and the nitrogen end of the molecule is more negative than the hydrogen end. Another way to draw this, let me draw it again so that we can put, now, in this case, what we're going to do is we're going to say in the nitrogen to hydrogen bond, the nitrogen end is more electronegative, so it gets a partial negative. That's a lowercase delta sign, and the hydrogen is partially positive. The lowercase delta, like an 8 that you don't finish, and it means partial. There's also an uppercase delta, which would mean change, but we're not using that one. We're using the lowercase delta in this case. Okay, so each of these three bonds is like that. And one way to do this is to say, if we kind of join all of the positive ends together, I could kind of show that as a little triangle here. The center of that positive bonds would be like right about there. The center of the negatives, well, there's only one, and it's right there. And those things are separated in space from each other, so therefore we have a polar molecule. The nitrogen end of the molecule is negative, and the hydrogen end is positive.